Alô? Alô? Eu levanto mais isso ou tá?
Acho que pode subir um pouquinho, só para...
Alô? Okay. Okay, so today is the second lecture of the mini course in Ratner's theory. Everybody registered in the workshop? Good. Okay. So I will start. Yesterday in the end, I think I went too fast. So I will start with the last of the talk yesterday. So let's make a review. So what did we see yesterday? Well, we saw many properties of the hyperbolic space. We saw who are the geodesics and who are the isometries and so on. We saw the structure also of hyperbolic surfaces, that if you have a surface which has constant curvature equal to -1, it is, what else? Connected and something else which I don't remember right now. Then X is going to be the quotient of the hyperbolic space by a discrete subgroup of isometries of the hyperbolic space. So, actually, if you assume that X is also orientable, then gamma is going to be a discrete subgroup of orientation-preserving isometries, which in other words means that gamma is a subgroup of PSL2R. Okay? So, this says that hyperbolic surfaces are the quotients of the hyperbolic space H by a discrete subgroup of PSL2R. Okay, so after that, our goal was to try to understand who are the geodesic and the horocycle flows on this system of coordinates. So first of all, we have to identify on which space these flows are defined, and they are defined on the unit tangent bundle, and if X is the quotient of H and gamma, then the unit tangent bundle of X is going to be the quotient of the unit tangent bundle of H by gamma. But yesterday we saw that the unit tangent bundle of the hyperbolic space is associated, it can be associated to the projective special linear group in 2 dimensions. Okay? So in other words, the space that we are working on is the quotient of PSL2R by a discrete subgroup. Good. So we have the geodesic flow on this space, and we have 2 horocycle flows, the stable horocycle flow and the unstable horocycle flow. So as I said, once we have that description of the unit tangent bundle as a quotient of groups, then we want to know how is the description, algebraic description of these 3 flows. And we saw that they are represented by multiplication on the right by some special matrices. The geodesic flow is the multiplication on the right by that hyperbolic matrix, e to the t over 2, 0, 0, e to the minus t over 2. The stable horocycle flow is the multiplication on the right but by that unipotent matrix, which is 1t, 0, 1. And the unstable is the multiplication on the right by the, again, a unipotent matrix, which is 1, 0, t1. Okay? So, from now on, you can actually forget the hyperbolic structure that you have. You can just think of a translation, a flow, which is a multiplication on the right, on a quotient space. Okay? So this is exactly the setup that I want to generalize today, which is the setup of Ratner's theorems. I want you to leave today understanding the statements of Ratner's theorems. Okay? So, before that, I just would like to make a remark that I spoke very fast yesterday, which is, what is the importance between the geodesic and the horocycle flows? So I said a few properties of the geodesic flow and the horocycle flow, and I said that they relate to each other because G renormalizes the horocycle flows. And what do I mean by this? I mean by this matrix identity. So if you look at this matrix identity, in other words, what you have is that the horocycle flow and the geodesic flow, they satisfy this equation. So the conjugation of HS plus with GT is the same as the conjugation of GT and H plus of at some other time. And this other time is specific, is S times e to the minus t. Okay? So you can see that GT is conjugating 2 horocycle times of the horocycle flow, Hs and Hs times e to the minus t. So we have that. Okay, so the conclusion is that H plus has zero topological entropy. Should I turn the light on, or is it okay now? Okay. So what we have is that GT Hs plus equals Hs e minus t plus GT. If I multiply by g minus t on the right here, it gives me that GT Hs plus g minus t is equal to Hs e to the minus t plus. So Hs plus, and I'm going to skip the H, the plus from now on, okay? Let's assume that we fix the stable horocycle flow. So this tells us that Hs and Hs times e to the minus t are conjugate. So if they are conjugate, in particular, their topological entropies are the same, right? So the topological entropy of Hs and the topological entropy of Hs times e to the minus t are equal. But we know that we can calculate the topological entropy of Hs in terms of the topological entropy of the time one map of the flow. The only thing that we need to do is to put out the S with absolute value. So this gives us that norm of S times topological entropy of the time one map is the same. If you do the same here, this is what we get. But this should hold for every S and for every T. So this implies directly that the topological entropy of the time one map, and hence of all times of the horocycle flow, is 0. Okay? So this is the conclusion that we have in this slide, that H plus has topological zero entropy, zero topological entropy, and the same happens to the unstable horocycle flow. Okay, so now I'm going to make a compilation of some properties of G and H to compare these two flows. So as I said yesterday, G is an anosov flow. So it has positive topological entropy. And actually there is a theorem of Ornstein and Weiss that shows that it is Bernoulli. If you fix any time, GT is always going to be a Bernoulli map. Okay? So also GT has many periodic points. This was proved by Margulis. He got exactly the asymptotics of the number of periodic points. So if you denote by pi of t the number of closed orbits, closed geodesics of length at most t, then Margulis proved that pi over t is basically e to the t over t. Okay, this is what is. So if t is large, this is also very large. So the number of the closed orbits is exponential on t. Okay? And because of that, G has many invariant probability measures, right? I mean, you can any of these closed orbits, they support invariant probability measures. If you have a lot of closed orbits, you have a lot of probability measures. Okay, these are the properties of G, and on the other side we have H. H has zero topological entropy, as we saw here, and it has few invariant measures. And what do I mean by this? I'm going to be more specific about this tomorrow, but just to make an example, is that if the quotient, the H mod gamma, is compact, Furstenberg proved that H is uniquely ergodic. So actually, it not only has few invariant measures, but it has only one probability measure. Okay? So it is on the other spectrum of G. Okay, so let me see if I want to speak of something else. And the reason for that, I said yesterday, but I want to emphasize it today, is that the geodesic flow is a flow which is a multiplication on the right by a hyperbolic matrix, while the horocycle flow is a multiplication on the right by a unipotent matrix. So this makes all the difference. And what we are going to see in Ratner's theorems is that we are going to change the space that we are acting on, X. In principle, we saw yesterday that it was H mod gamma. Now we are going to consider the quotient of a Lie group by a lattice. and we are going to change x by this, and we are going to change the horocycle flow, which is a specific case of a unipotent flow, to general unipotent flows. Okay? So this is the role of Ratner's theory. Is exactly under this setup of the action of unipotent flows on quotients of Lie groups by lattices to be able to classify, to get rigidity results in the sense of orbit closure, measure classification, and also equidistribution. So the theorems, they are these three things that I put here. And the aim of today is exactly explain each of these terms that you might not understand so far. So what is a homogeneous space? What is a Lie group? I'm going to also to say what is a Lie group. What is a unipotent element? And what does it mean to be U homogeneous? So this is the first one of the theorems of Ratner, is the orbit closure theorem. The second one is the measure classification theorem. So there is a new term here that I'm going to define to you, and that is what it means to be algebraic. And the third theorem is on equidistribution. So here there is a new term which is eugenetic, and our goal is exactly to clarify what are these red expressions. Okay? Any questions so far? No. Okay. So we are going to stop and we go to the blackboard right now. So first of all, I'm going to define what are homogeneous spaces. And for that, I need to define what is a group action. So group actions. And our setup is always going to be the following. G is a locally compact Hausdorff topological group. Actually, in a few minutes, it's going to be only a Lie group. And X is a locally compact Hausdorff space. Okay? So we say that G acts on X on the left, let's say. So a left G action is a continuous map that does the following. It gets an element of G, it gets an element of X, and it gives you back an element of X. So it's a map like this. And we are going to denote the image of the pair Gx under this map by Gx. Okay? Without comma, without anything. So it is a continuous map like this that satisfies the group structure. So to satisfy the group structure, I mean that first, the identity here acts, the identity of the group acts as an identity of X. So it means that Ex is equal to X for every X. And the second one is that it satisfies the group operation in the sense that if you get, and I said this yesterday, I think, if you get X and you act by H, and then you act again by G, this is the same as acting by GH. Okay? So this is a left G action. We can define also a right G action. And instead of G being on the left, G goes to the right. So it's a continuous map X times G that goes to X, that for every pair of points, one from X and the other from G, I get a new element of X, which I'm going to denote by XG. Okay? So it's a continuous map, also satisfying the compatibility with the group. So XE equals to X, and X, if I act on X by G and then I act by H, this is the same as acting by GH. Okay? So this is a right action. And actually there is no distinction between left and right actions. Because if this guy here is a left action, gx goes to dx, then I can construct a right action just by using the left action, but instead of multiplying by g, I multiply by g to the minus 1. So this action, this is a new action, which is defined on the product x and g. And this is going to be, because the initial action is left, is a left action, this one is going to be a right action. Okay? So whenever you have left actions, you have right actions. And you could fix one of them to work with. And I'm going to do this from now on, and I'm only going to be working with right actions. Okay? Good. Okay, so what do I have to say about Lie groups? And what is a Lie group? First. So a Lie group, G, it is a smooth manifold that is also a group. So with a product operation, let's say, but this product operation has to be smooth with respect to the Riemannian metric of your manifold. So the assumption that you require is that this map here that gets two pairs, GH, and sends back to G by multiplying by G and by H minus 1, this guy is smooth. Okay? So it is a group which is also a manifold. For example, Rn, or as we saw yesterday, SL to R, or you could consider any special orthogonal group, SON, and so on. Okay? So once you have these things, you have two special maps on your Lie group, which are the translations. So you have the right translation, which is a map RH, and what does it do? It gets an element of the group and multiply by H on the right. Okay? And we have a left translation. Which instead of multiplying on the right, it multiplies on the left. Okay? So the assumption on the smoothness of this map here guarantees that both these maps are also smooth. Good. Okay, so I said that Lie group is a smooth manifold, so we could have we have a lot of distances. We can make geometry on this group. But being a group, we would hope to have some distances, some metrics which are more important than others. And actually there are some distances which have a lot of symmetries in the sense that they are invariant by either these translations or these translations. Okay, so I'm going to show you how to construct distances on Lie groups which are either left invariant or right invariant. And the way to do this is the following. If you consider any inner product on the identity, so it's an inner product on the tangent space of the identity of the group. Okay? And now I want to define an inner product on every element of the group. So, if you give me two vectors which are in the tangent space of some element of the group, I define VWG, the inner product of V and W, as. So what you do is to use the left translation to send these two vectors back to the identity, because in the identity you know how to measure, you know how to consider inner products. So if you want to put these guys back to the identity, you should apply the left translation by G minus 1. So you get the left translation by D minus 1 at the point G, and you act on these two vectors, V and W. And now, because the left translation sends, this left translation, L G minus 1 sends G to the identity, these two guys, they are vectors that belong to the tangent space of the identity. And in the tangent space of the identity, you can consider the inner product. So you define like this. Okay? So this is a way of using the symmetries of the group to define an inner product, a metric in your group. And the main property, this equation actually tells you that left translations are all isometries. So with this property, with this definition, each left translation is an isometry. So, if you consider the distance induced by this metric, then to say that these guys are isometries is the same as saying that if you want to compare the distance between HD1 and HD2, this is the same as comparing the distance of G1 and G2. So this is what I call a left invariant distance or a left invariant metric. Okay? These are the distances I'm going to be working with in Lie groups. I could have chosen right invariant distances, but I decide to choose left invariant. And you're going to see, if you read the lecture notes, you're going to see why. Okay, so we know we have Lie groups, we know how to measure distance between points, and we know how to do that in a satisfactory way, in the sense that it satisfies this property. LH is an isometry for every H. Okay. So in order to do ergodic theory, we have a space, we have even better, we have a distance, but we need measures, right? So what I'm going to do now is to show to you that Lie groups, and actually more general, locally compact house of topological groups, they have some special measures, which are also compatible with the group structure, in the sense that they are invariant under these translations. So now let's talk a little bit about Haar measures. So as we did with distances, we can consider a lot of measures here in our group. But the group structure suggests us to look for some special measures. For example, if you want to compare the measure of a set X with the measure of a set of its image Gx, so you get X and you apply the left translation by G, in general, measures are not going to satisfy that these two guys are the same. And you could actually require to have the same thing for the right translation. So is it true that you have measures that satisfy these properties for every Borel set X and every G? Well, in general, it's not true. These two assumptions are too strong, but at least you can get a measure that satisfies this for every G and for every X. And even more, this measure is going to be regular in many senses. So this is what is called the Haar measure. So here's a theorem that there exists a measure mu on G such that a few properties are satisfied. So the first one is that equality that I just wrote, that mu is left invariant. Which means that the measure of a set is the same of the measure of its left translate by any element of the group. Okay? The measure is also locally compact in the sense that the measure of any compact is finite. Okay? And you can approximate the measure of a set both from inside and from outside. So I have two more properties to say about Haar measures. The third one is that mu is inner regular. Which says that if you want to measure a set X, you could only consider measures, you could only get it from measuring subsets of X. So mu of X is the supremum of mu of K, where K is a compact subset of X. And the last property of this measure is that it is also autoregular. Which says that you can also recover the measure of a set by measuring sets that contain it. So the measure of X is also the infimum of the measure of A when you run over all sets A that contain X and are open. Okay? So there is always one measure satisfying this. And furthermore, this measure is unique up to a multiplication by constant. Okay? So this is a very special measure. Mainly because it is invariant under left translations. Well, we could apply the theorem to get also a right invariant measure, right? It's a measure that satisfies 1 when you change here gx to xg, so it's right invariant, and also satisfies 2, 3, and 4. But we are going to work only with left invariant measures. So this measure that is guaranteed by this theorem is going to be called, we call mu the left Haar measure of G. Okay? So let us give some examples of Haar measures. So some examples. For example, what is the Haar measure of Rn? Mario? Huh? Lebesgue. Lebesgue is invariant by translations. Exactly. What is the Haar measure? Let's say that we have a homomorphism between two groups. So what is the Haar measure of H in terms of the Haar measure of G? Well, if you have a Haar measure here, then you could push this measure to H under the homomorphism. And because it is a homomorphism, this new measure is going to be invariant by translations of H. So actually, the Haar measure. So let's denote, let's put an index here to mean that the measure is the Haar measure related to G. So with this notation, the Haar measure of H is the push forward of the Haar measure of G. Okay? Good.
In the case of a compact in H, we have a premajor with an infinite measure.
Huh?
But in that case, the compact in H, we have a premajor G that has infinite measure.
Yes. Wait. So I'm sorry, what did you say again?
The premajor of a compact of H.
Ah, yeah, that's right. Yeah, so I should go here and maybe to fundamental domains. So this is not true. So let's just delete it. And let's go to a third example, then I'll check this later, okay? So let's go to a second example, which is, I want you to remember two subgroups that I considered yesterday. One of them is A, it's the diagonal subgroup. So lambda 0, 0, lambda minus 1. And the other one is U plus, is the unipotent subgroup. 1, B, 0, 1. Okay? So let's write it here. This is the set of lambda minus 1. Let's put A. And this is the set 1, B, 1. So what is the Haar measure of A, for example, under this parametrization? Huh? Well, you can consider, you can remember that this guy here, if you consider sending this matrix to log of A, then this is going to give you a isomorphism between, okay, so if you have an isomorphism, that condition is true. The isomorphism sends one measure to one Haar measure to the other. So if you construct an isomorphism between this and the real numbers, which you can do it by just sending this matrix to log of A, the Haar measure of this guy should be the pullback of the Lebesgue measure, which is the Haar measure on R. So the Haar measure of A, if you do this, I mean you are applying log. So the Haar measure of A here can be written as 1 over A times dA, if you do a change of variables. And the Haar measure of U plus, well, this guy naturally is identified with the real numbers, right, with R. So it's just, under this parametrization, is dB. Okay? Tomorrow we are going to see how to get Haar measures of products. If you have some structure of two subgroups, and you know who are the Haar measures of these two subgroups, you could consider the Haar measure of the product. In this case is going to satisfy the conditions that I'm going to explain tomorrow, but then the conclusion is that the Haar measure of the product group A, U plus, is going to be the product of the Haar measure. So it's going to be 1 over A, dA, dB. Okay? So just observe that A, U plus is equal to all the matrices of this form. A, B, 0, A minus 1. We are going to need this for tomorrow, for the proof of Furstenberg's theorem. Okay, so we have many examples of Haar measures. So now we have Lie groups, we have distances, we have measures. But in general, this space is not compact, right? And we would like at least to do ergodic theory. And to do ergodic theory, I mean, the ideal situation is to have compact space. But we cannot consider, sometimes we cannot have that, but we should at least have finite measure. And this is not the case of the Lie group. So what we are going to do is to mod out to consider quotients of Lie groups by some discrete subgroups. Just like we saw yesterday, hyperbolic surfaces are an example on which you have a quotient of a Lie group, which is the hyperbolic space, by a discrete subgroup, which was the deck transformations, the group of deck transformations. So now I'm going to talk a little bit about quotient spaces. And lattices. So let G be a Lie group, and let gamma be a subgroup of G. Okay? So there is an equivalence relation which defines the quotients, the quotient of G by gamma on the right. So say that two elements, GH, are equivalent if you consider G times H minus 1, and this belongs to gamma. Okay? This is an equivalence relation, and the equivalence classes are called the right cosets. So an equivalence class of this equivalence relation is called a right coset. We are going to denote it, and we already did this yesterday, by gamma G. This is going to be the right coset associated to the element G. And the space of right cosets, I'm going to denote by G mod gamma, and we write like that. So this is the space of cosets, and it's called quotient space. Okay? In general, even if G is a Lie group, this might not give us something which is smooth. To have that this quotient is smooth, we should assume something about gamma. And the assumption is discreteness of gamma. So assume that gamma is discrete, which means that for every G, for every, let's say, gamma in gamma, there exists an epsilon such that when you look at the ball around gamma of size epsilon and you intersect with gamma, the only element of this intersection is gamma itself. Okay? So around every point you could put a ball which is disjoint from anything else of gamma. And actually in the case, because this guy is a subgroup, this epsilon is going to be universal. You could choose the epsilon to hold for every gamma of your group. Okay, so this is what it means to be discrete. And whenever you have a quotient of G by a discrete subgroup, the quotient is a smooth manifold of same dimension of G. Okay? For example, well, you could consider G to be equal to R, and gamma should be discrete, so you consider to be equal to Z with the additive structure. So this quotient, we know that is the unit, the one-dimensional torus. Okay, so this, and we know that it is a smooth manifold of same dimension as of R. Okay, so we are in the direction of getting something that has finite measure, but we don't even know if it has a distance involved on it. So let's show that actually there is the left invariant distance of G can be induced to this quotient And the definition of the distance is very simple. It is a little bit annoying to check that it is actually a distance. So, given D, the left invariant distance on G, define a distance on the quotient by the following. So the distance on the quotient gets two elements of the quotient and gives me back a number, positive number. So how am I going to do this? I am going to consider to fix one of the points, G, and to run over all the possible representatives of this coset here. So what are the possible representatives of gamma H on the group G? Well, they are the elements gamma H, right? Where gamma runs over all possible elements of gamma. So I'm going to consider the infimum of these guys. Okay? So with this definition, and here is where we are using the left invariance of the distance D. By the left, for example, how do you show that this guy is symmetric? Well, you write it here with G exchanged by H, and then you could look at this and send the gamma here to this left side. You are using the left invariance. But once you put to the left side, it gets gamma to the minus 1, but makes no difference to run over gamma minus 1 or gamma, because the big gamma is a subgroup. So then you're going to get that, for example, this distance is symmetric. So here we actually use the left invariance. Furthermore, it's going to satisfy that it's going to be equal to 0 if and only if the two cosets are the same, and it satisfies the triangle inequality. So this guy is a distance on the quotient, which is not right invariant, is not left invariant, is nothing. Actually, I could not even ask about left invariance. Why? Because to ask about left invariance, I should have a left action, right? But I don't have left action on this quotient. So on gamma mod G, I have an action of G on it, but the action is the right action. So note, G acts on the right quotient on the right. How do I do that? I get an element of G and I get a coset, and I simply plug into G on the right of H. Okay? It is easy to check that this actually does not define of the coset here, of the element H here. So we have a right action on this quotient. So for example, we could ask if this distance is right invariant with respect to the G action. It is not. Okay? It is just a distance. But at least we have a distance, which is well defined. And the question now is whether we have a measure. Hopefully we do have. And the measure is going to be defined by the Haar measure of the group. But before, I have to talk a little bit about fundamental domains. So what is a fundamental domain? Of the subgroup gamma. And a fundamental domain, it is a Borel subset of your group, okay? Such that if you get your Borel subset and you begin to translate it by the elements of your subgroup, you get a tessellation of the group G. So it is a Borel set F. In other words, what I just said is that G can be written as the disjoint union of the translates of F under elements of gamma. Okay? So this is the definition of a fundamental domain. And I have here two pictures of examples. For example, on the left, I have the fundamental domain of something which is actually going to give me that G mod gamma is going to be compact. Basically because the fundamental domain is going to have finite Haar measure on the hyperbolic space. And on the right, I have a fundamental, each thing with the same color there is going to be a fundamental domain of the modular surface. So that thing which is like this, and the other purple, and the other yellow, and so on. On that case, we are going to have, because this fundamental domain is going to go to infinity, we are going to have something which is not compact, but also again, but at least has finite measure. Okay? So this is a fundamental domain, and I don't remember if every discrete subgroup has it, but every nice subgroup has a fundamental domain, and actually it has a fundamental domain on which the boundaries are geodesics of your space. So in the case of the hyperbolic space, for example, all of these lines that you see on these pictures, they are geodesics of the hyperbolic plane. Okay, so we always have fundamental domains, and using them, we can construct invariant measures on the quotient. And the main observation is the following. Is a lemma which says that if you consider, so before stating the lemma, let's just introduce a notation which is the projection. So let pi be the projection that goes from G to G mod gamma. And the lemma says the following. Says that if two subsets of G satisfy two things. The first one is that when you restrict the projection to B1 and when you restrict the projection to B2, you get bijections.